Hi everyone, my name is Ligia. This is a joint work with Marie-Vetcoms, and this talk will be about box-Coq transformations and bias reduction in extreme value theory. The outline of this talk will be we start with a brief introduction where we present the basic framework in extreme value theory in a semi-parametric framework, and we also address the box-Coq transformation. Next, we present the box-Coq estimator. We prove its consistency and the syntactic normality, and we also address the estimation of the box-Coq parameters. The finite sample behavior of the estimators will be presented through a small-scale Monte Carlo simulation studies, and some concluding remarks are also presented in the end. So, we all know that in statistical literature, the box-Coq transformations are used to make the data more suitable for statistical analysis. And we know that under an extreme value theory context and working in a semi-parametric framework and with Pareto type tiles, which means that we are working with models with a positive extreme value index, we know that the most known extreme value index estimator is the yield estimator. And this estimator is usually biased and sometimes presents an erratic behavior in graphical representations. So, to account for this bias, several techniques have been used to reduce the bias of the estimator. And in this work, we are going to propose a new technique to remove the bias of the yield estimator. That is the use of the box-Coq transformations. So, we are going to work with random samples of n IID random variables with distribution function capital F and density function Fx, and we are going to denote by this the associated ascending order statistics. We know by Fisher and Tippett that there exist sequences of real constants an and bn such that the maximum linear normalized converges to a non-generate random variable, and this variable is necessarily of the type of an extreme value distribution function with shape parameter xi. Then we can then say that capital F belongs to the max domain of attraction of an AV xi, and we use this notation to denote it. The parameter xi is the extreme value index, is one of the primary parameters of extreme events, and it measures essentially the weight of the right tail. So the heavier the tail, the greater xi is. The box-Coq transformations, they were proposed by Box and Cox in 1964, and they essentially are a power and shift transformation of the original data. There have been several applications of the box-Coq transformations in extreme value theory. We have here some of them. We are going in this work. We are going to use the findings of Wadsworth and co-authors in 2010 and of Taylor and Verlow in 2004. So, following Wadsworth and co-authors in 2010, if we apply a box-Coq transformation to the original sample and define the maximum in this way, and assuming that the maximum xn of n linearly normalized converges to an extreme value distribution function with index xi, then we have the same type of behavior for the maximum yn of n, but now with a shape parameter xi star. And then we can say that capital F is in the max domain of attraction of an extreme value distribution function with index xi star. If we further assume that the distribution function of the original sample is twice differentiable for large values of x, then we can relate both shape parameters xi and xi star. Note that if Xi is 0, or if is smaller than 0, then we know that Xi star will always be equal to Xi and will remain in the same domain of attraction. But if Xi is positive, Xi star, we can no longer guarantee that Xi star is equal to Xi. So we can start in a Frechet domain of attraction and apply a box-Coq transformation, and we can no longer be in a Frechet domain of attraction. So as we are going to work under a semi-parametric approach, we have the usual notations associated with the semi-parametric approach, and we have also to consider two conditions. We have a first order condition that allows to guarantee the consistency of the estimator. So we know that F belongs to the max domain of attraction of an extreme value distribution with index Xi if and only if the quantile function is of regular variation in index Xi. We are going also to assume that a second order of condition of this type holds, where rho is the second order shape parameter and A of t is of regular variation in index rho. So as I said before, we are going to work in the Frechet domain of attraction, which means that we are working with Pareto type tail models with an extreme value index positive, and we are going to consider a wide class of models within the Frechet domain of attraction, that is the Allen-Welsh class of models. This is a class where the tail quantile function can be written in this way, and this function A of t that appears in the second order condition can have the following parameterization. So Teugels and Veron, they considered box-Coq transformations, box-Coq transformations of this type that generalizes the classical box-Coq transformation, and they use the theory of regular variation to study and to choose the best value of sigma in order to increase the speed of convergence or the rate of convergence in the second order condition. So using this box-Coq transformation, we can now rewrite the first and second order condition. And regarding the first order condition, we can say now that U star, that is the quantile function that is associated with the transformed random variable, is of regular variation in index Xi star, which is equal to Xi times sigma. And regarding the second order condition, the authors prove that choosing sigma equals to minus rho over Xi would enable to increase the rate of convergence of the second order condition, and propose the box-Coq estimator, who has this functional form here and is a generalization of the estimator, which is average of the log excesses. So note that we have here a power transformation and a shift transformation, and we have to guarantee that our data is strictly positive. So sigma is always positive and A must be also positive. Note also, as we are going as estimator, as we are going to estimate Xi, we need to divide once more by sigma in order to have consistency to Xi. So these both estimators, they are consistent for the estimation of Xi when considering intermediate sequence of integers, sequence k such that k goes to infinity and k over n goes to 0. So we can now present the asymptotic behavior of the box-Coq estimator, assuming that we are working with intermediate sequence of integer and that the second order condition also holds. So note that we have here in green the distribution representation associated with the estimator, and here we have an extra bias term that can reduce the bias of the estimator. Zk is a symptotical standard normal, and if square root of a k, a of n of a k goes to lambda, we can also guarantee this type of behavior. If we look to the main component of the bias, we can see that if we choose A equals to B times C to the power sigma, we can, the Box-Cockle estimator is now a reduced bias extreme value estimator, and we have this type of behavior. So the Box-Cockle estimator is a reduced bias extreme value estimator who has the same variance of the estimator. So he is a minimum variance reduced bias estimator. Regarding the Box-Cockle parameters, as we are working in all large class of models, we can easily obtain the Box-Cockle parameters for several models that belong to this class, like the BERT, the Fred-Shea, log logistic, generalized Pareto, Cauchy, student T, among others. Note also that for some of the models, like the BERT, the log logistic, and the generalized Pareto, we can write the reciprocal quantile function of the transform variable in this form. And for this type of models, we can prove that the Box-Cockle estimator is asymptotic and biased for any k value, not necessarily intermediate. A second remark, that this Box-Cockle estimator is also a generalization of an extreme value index estimator that was proposed by Gomes and Oliveira in 2003, where the authors imposed a shift A to the data in order to choose the best A that enabled reduction of the bias of the yield estimator. The estimation of the Box-Cockle parameters is very important. We are now we are going to propose in this work and to estimate adaptively the parameters, the Box-Cockle parameters, sigma and A, but we are now deriving the maximum likelihood estimates of sigma and A. So we are going to consider for an estimate of sigma, we are going to consider an estimate of rho, an estimate of rho computed on the I-level K1, where rho at is the class of estimators that was introduced in Fragals by Fragals and co-authors in 2003. And for an estimate of Xi, we are going to use the estimator computed at the level that minimizes asymptotic mean square error. We could also use others estimates for Xi. And for the estimation of A, we are going to consider a misspecification of the first order scale parameter C. We are going to consider to put C equals to 1. And so we are going to use for the estimation of A, the class of beta estimators that was introduced by Gomes and Martins in 2002. The classes of the second order shape and scale parameters, they are well derived, and we have here the asymptotic behavior of both classes, and taking the asymptotic expansion into consideration, we were able to prove that the Box-Cockle estimator, when we estimate properly the Box-Cockle parameters, the Box-Cockle estimator is still a minimum variance reduced bias EV, extreme value estimator. So we are going to show the finite sample behavior of the Box-Cockle estimator. We have considered here a small scale Monte Carlo simulation study with 1,000 runs, and we have here the simulated patterns of the mean values, expected values or mean values, and mean square errors. We have considered the yield estimator, that is this line here in black. We have also The box calculus estimator, assuming that the parameters, the box calc parameters are known, assuming that they are adaptively estimated. And we have also plotted here the corrected yield estimator that was introduced by Cairo and co-authors in 2005. So we have here for a student T2, we can see that we have to look to the blue line and to the magenta line. We can see that regarding the bias, both estimators, they have a similar behavior, similar bias until k equals to 400, but from this value till from this value on, we see that the bias associated with the box calculus estimator is smaller than the one of the corrected yield estimator. If you look here, we have on the top panel, we have a Burr model with psi equals to 0.25. And on the bottom, we have a generalized Pareto with psi equals to 1. Note that for these models, the box calculus estimator is asymptotically unbiased for all k values. We can see here on the orange line here, when we compare the blue line and the magenta line, we can see that for the Burr model, the box calculus estimator has a smaller bias. And for the generalized Pareto model, both estimators, they have similar bias until values of k equals to 600. And from that value on, the box calculus estimator, it presents a smaller bias. We don't see much difference regarding mean square errors. So some concluding remarks. We can see that when we apply a box calc transformation on the data, we can increase the rate of convergence of the tail of the distribution. And as a byproduct, the bias of the estimation procedure is reduced. So the class of the box calculus estimators is a class of reduced bias of estimators that has the same variance of the estimator, being thus a minimum variance reduced bias of estimator. So the preliminary simulation studies, they show that box calculus estimators, they compare favorably with the corrected estimators for several models. We also know that the estimation of the box calc parameters can be improved, and we are now deriving the maximum likelihood estimates. And this methodology, the box calc transformation, can also be used to obtain other estimators of parameters of extreme events. So thank you for your attention. I have here the main references, and thank you.